from here. Last period I hung up on the class, but they were still in the meeting, so that was good. What are you going to do with me? There I am. All right, let's talk about what you were supposed to do last night. Oh, and I got heckin' darn. So, yeah, I've just been goofing all day today. Let's get these out of here. It'll look kind of similar, but I don't need all those doodles on yours. There, you had the whole lecture. You get to see all the slides now. Okay, those didn't save. How strange. I give up. Okay. Here we are. All right, so for homework last night, you were supposed to do the last 4 in set number, in the multiple bond set. It didn't have a number. Both of these, I'm going to do them at the same time. Both of these have 2 carbons, but they have different number of hydrogens. How strange. Well, it turns out carbon likes to multiple bond. It'll single bond, it'll double bond, it will drive you crazy. So we will do a little bit on hydrocarbon chemistry, organic chemistry, but that'll be a while from now because we're going to go back and do metals next week. So 2 carbons. Remember, carbon can bond more than once, so always put the carbons next to each other. That's a really big, important piece. Never put hydrogens in the middle. They can only bond 1 time. This first one has 4 hydrogens, and the question usually is, well, what do I do with them? Do I put 3 of them on this carbon and 1 on this one? Just make them kind of symmetrical. And it doesn't have to be, it really doesn't matter if you put them top or bottom, left or right, but do put, if there's 2 carbons and 4 hydrogens, put the same number on each one for this point in time. Okay, hopefully you noticed that there were unpaired electrons, and hopefully you realize, since this was about multiple bonds, that those electrons need to shift to the space between the 2 carbon atoms because they'll be attracted to those nuclei. Okay? So what does that do for carbon? Well, it gets carbon its octet. Carbon has, this would be blue actually. So carbon has 1, 2, 3, 4, plus 2, 1 from each of the hydrogens, plus 2 from the other carbon. It will get its octet, and each hydrogen gets its duet when there's a double bond. Okay, 2 for each of the hydrogens, 1, 2, 3, 4, 5, 6, 7, 8 when the carbons share 2. So that, there's a whole nother naming system for hydrocarbons. 1 carbon is meth, like the drug. 2 carbons is eth, 3 carbons is prop. So this would be ethene, just little coming attractions. You don't have to know that yet. And then this one also has 2 carbons. But it only has 2 hydrogens. And those 2 hydrogens, again, when in doubt, just make it so that they are symmetrical. Slap those 2 hydrogens on either side, or at least on different carbons. And then again, you probably realize these unpaired electrons need a buddy. And so they're going to sidle up in here and create a triple bond. Carbon is a substance, element that makes triple bonds, as does nitrogen. So those triple bonds then allows each carbon to have their octet by sharing 3 electrons with 1 carbon and 1 from the hydrogen, along with their own 4. And so hopefully some of you got that there's a triple bond here that is called ethine. The F tells me 2 carbons, and the YNE tells me a triple bond. Again, coming attractions, I'm getting ahead of myself. All right, this one might have caused you some trouble. I hope not. The formula shows the hydrogen between carbon and oxygen. Never, ever, ever put hydrogen in the middle. So you should have put down the carbon. And then oxygen has 6 valence electrons, as you know. So they're sharing an electron, that's fine. That gives oxygen only 7, that gives carbon only 5. The 2 hydrogens, just get in the habit of putting them on carbon. So now carbon's up to 1, 2, 3, 4, 5, 6, 7, as well as oxygen, but that's not what they want. They want 8. So hopefully you saw those unpaired electrons, and they're going to migrate as well and create a double bond. And again, that gives each atom, except for hydrogen, their octet. So again, the best hydrogen can do is a duet, 2 of them. Carbon has its 4, plus 2 from oxygen, plus 1 from each of the hydrogens to get 8. Oxygen has 6 of its own, and then 2 from carbon to get its 8. So there's a double bond here. Any questions so far? How we doing? Pipe in if you need explaining. Hopefully this is good enough. This is CN, and you might recognize that as cyanide, the polyatomic ion. And then this is hydrogen, and so you might think this is ionic, but it's not. It is a covalently bonded compound in this case, because these are all nonmetals. So HCN, this one kind of hints at the fact that you're going to put the carbon and the nitrogen next to each other. And again, remember, nitrogen has a lone pair. It has 3 unpaired electrons. So the first bond is going to be sharing between carbon and nitrogen. Remember also that nitrogen likes to make triple bonds with other nitrogens because it is a diatomic gas in our atmosphere. All right, I have 1 hydrogen. That's not enough, right? So let's see what happens. So I'm going to put the hydrogen on carbon again, because that's usually where it's going to be. You'll notice there's unpaired electron, unpaired electron, unpaired, unpaired. So 2 from carbon and 2 from nitrogen. And magically, hopefully, oh heavens, please forgive me if I don't write it. Hopefully you got a triple bond. Hopefully you got a triple bond between the nitrogen and the carbon. Nitrogen contributes 3 to carbon's 4, and then 6, 7, 8, boom. And then nitrogen has 5 and borrows 3 from the carbon to get its octet, and again hydrogen is 2. All right, questions? How we do? Piece of cake, easy peasy, lemon squeezy. What do you guys think? Was it good? Anybody get them all right? Pretty good, miss one. Okay, thank you, Chuck. Triple bonds causing problems. What was the problem? Anybody? Give me some clues. Good, thank you. Good, pretty good. All right, pretty easy. Good, Colin. All right, let's move on then and get on to the next topic, which is bond association energy. Bond association energy, just you could probably deduce what this means using your English skills. It's something about bonds between atoms. Dissociate is when they come apart into pieces, and how much energy it takes to do that, right? So very simply, it's how much energy do you need to break a covalent bond between 2 atoms. So normally a covalent bond involves sharing of 2 electrons, 1 from each atom, We saw yesterday that's not always the case, and I'll talk more about it next week. But you should realize that, I hope that if there's one string holding things together versus two strings holding things together versus three strings holding things together, there might take a different amount of energy to break all of those, okay? And that's what we find. So also, this is not rocket science. The bigger the number, the larger the dissociation energy, the stronger the bond. No-brainer, right? You also would probably be able to figure out that a double bond would be stronger than a single bond. However, it's not exactly 2 times. I don't think there's any example where it's exactly twice as much as a single bond. Also, triple bonds, again, would be stronger than a double or a single bond, but they're not going to be exactly 3 times. And it's really weird. Sometimes it's less than twice as much or less than 3 times a single. Sometimes it's more. It just is. So this is all done by experimentation and measuring the values. And there's tables and tables of them. You don't need to memorize them. That's not important. You just need to know that it exists. Also, the way we measure energy, of course, in science, in the metric system, is using joules, because that's such a tiny amount. We need thousands of them, so kilojoules. And when we're dealing with atoms and molecules, they're so tiny, we need lots and lots, quadrillion millions of them. So we talk about kilojoules per mole when we talk about the energy amount. And then in college, you'll probably get into discussions about bond length. What I want you to notice just here is that as you go from a single to a double to a triple, it's longer, shorter, shortest. Single, double, triple, longest, shorter, shortest. So that pattern continues in all of these situations. So carbon, nitrogen, and oxygen are elements that will form multiple bonds with each other and with themselves in the case of carbon and nitrogen. So real quick, carbon-carbon, single bond, 346 kilojoules to break. Double bond, 612, a little less than double, right? Triple bond, 835, again, a little less than 3 times as much, but still more than the others. Same thing with carbon to nitrogen, 305, 615, 887. You guys can read the numbers. Triple's the most, double is medium, single is the least. That pattern holds all the way through. When you get to carbon with oxygen, it's still the same. Shorter and shorter, more and more energy. And so the energy, what's happening is the atoms are really literally pulling in tighter to each other because the nuclei are fighting over those electrons, if you will, and it's harder to break them. The one that's really interesting is nitrogen. Look at this. So really low, the lowest one on this list, energy to break a single nitrogen to nitrogen bond. More than double to break a nitrogen-nitrogen double bond, and 5 times as much to break a triple bond. And again, nitrogen is triple bonded in our atmosphere. It's hard to break it apart. It takes a lot of energy. Not as much energy as this, but still a lot. Excuse me. Excuse me. Okay, so again, bigger numbers, harder to break, stronger bonds. Okay, triples are always more than doubles. Doubles are always more than singles. There's a concept, this is a weird concept. So those of you that sing, or those of you may have heard this term, like someone's has a very deep resonant voice, you know, kind of their vocal cords vibrate a lot. That's how I visualize it. It resonates with you, you know, it makes sense to you. This idea of resonance is an explanation for what the heck's going on in oxygen, whether it's diatomic oxygen or ozone oxygen. So we've already looked at the fact that oxygen that you need to stay alive, that you breathe, sorry, that was so small, is double bonded. But if you remember a day or two ago, the table said not complete or not the right answer. And it's close enough for us. It's plenty good enough for us, and it satisfies the octet rule. However, there's some other weird stuff going on, and that's more apparent with ozone. So we're going to talk about ozone. It's also a really important environmental problem, the hole in the ozone layer, and I want you to be aware of that. The NGSS, the new National Next Generation Science Standards, really incorporates a lot of earth science in here, but I've always talked about this with my students. So let's talk about why we're talking about ozone. Well, first of all, what the heck is ozone? Where is it? How does it form? Here's a quick video on that. The guy talks pretty soft. He's got a British accent, so hopefully you can hear him. Not this one. That's physics. Wait. And I'm going to find it. I promise I am. There we go.
In this video, we will learn about the two main layers of our atmosphere. The troposphere, full of weather and bad ozone, and above that, the stratosphere, where good ozone protects us against dangerous ultraviolet light. Our atmosphere is made up of gases, mostly nitrogen and oxygen. They're held to the Earth by gravity, a sort of ocean of air. Because air is compressible, it gets less and less dense as you get further from the Earth. Let's consider the first 50 kilometers where 99% of the atmosphere is found. Visible sunlight passes through the atmosphere and warms the ground, heating up the air at ground level. As the colder air above sinks, it pushes up the warmed air, which is less dense due to expansion. This movement, known as convection current, gives us our weather systems. The atmosphere gets colder and colder till you reach about 10 kilometers, the tropopause, where the temperature is coldest. Below this is the troposphere, containing 80% of our air and all the weather. Above the tropopause, we have the stratosphere. This is a layer of thin air which is hot on top because it's heated from above by ultraviolet radiation absorbed by the good ozone and cold underneath, making it dynamically stable. Contrast this with the turbulent troposphere. If you have ever flown in a jet aeroplane, you may have had a bumpy ride after takeoff through the turbulent troposphere. But once you're above the clouds, above the weather, your journey is smooth. Propeller planes cannot fly this high because the air is too thin for the propeller to grip the air. So where does this good stratospheric ozone come from? Pause the video and think of the formula of ozone.
We already did that. So.
Well, ozone is an allotrope of oxygen. Its molecules are made of 3 oxygen atoms bonded weakly together. It is an unstable gas which slowly decomposes back to molecular oxygen. The ozone in the stratosphere is continually being made and broken by the ultraviolet light in the ozone-oxygen cycle. To start with, UV gets absorbed in the stratosphere by molecular oxygen, which splits into 2 fast-moving atoms. These fast-moving oxygen atoms collide with air molecules around them, nitrogen and oxygen. This slows the free oxygen atoms down, enabling them to bond weakly with the molecular oxygen to form ozone. If they're moving too fast, they simply bounce off. The energy they shared with the molecules in the air heats up the upper atmosphere. The oxygen atom has now joined with an oxygen molecule to form ozone. Ozone is very effective at absorbing ultraviolet light, which causes the ozone to split back into an oxygen atom and an oxygen molecule again, keeping the upper atmosphere warm. Ozone reforms as before once the oxygen atom is moving slowly again. The ozone is spread out through the stratosphere, shown here in black. Why do you think there is so little ozone high up and low down? Remember, we need ultraviolet radiation and oxygen to make ozone. Pause and think. Well, here there is too little oxygen, and here, near the tropopause, the point of lowest temperature, when the atmosphere and the stratosphere join, there is no ultraviolet light available. It has all been absorbed by the ozone further out. So this is the ozone layer. If the ozone was squashed together like a solid, it would only be the thickness of a sheet of cardboard, but it is actually a gas spread out over 20 or 30 kilometers. Before our atmosphere was filled with oxygen, the UV reached the Earth's surface and prevented life from emerging onto the land. Ozone is also present in the troposphere, formed mainly by the action of sunlight on pollution from motor vehicles. Here, it helps to form photochemical smog and is a pollutant.
Okay, so that gives you an introduction. And I think some of you probably took Earth Science as freshmen. Maybe some of you did not, and maybe you remember, maybe you don't, but there are multiple layers of the atmosphere, and those layers are distinguished by changes in temperature. So the place where everybody, all life forms exist is the troposphere. The boundary between the troposphere and the stratosphere is called the tropopause. So there's also a stratopause before the mesosphere, and there's also a mesopause before the thermosphere. And he's saying the thing is that it's really hot up here. You got to keep in mind that that is a reference to the temperature, which is the kinetic energy of the particles. So yeah, the kinetic energy is really high, but there's very few atoms and molecules up here. So it would not feel warm to you. They're basing the temperature on the few particles that are there. Okay, they have to hit you to make you feel warm, and there's not really enough of them. It would be chilly. Okay, so it's cold at the bottom. Excuse me, wrong one. It's warm at the bottom, and then colder at the top. And then what happens is that changes. That as you go up through the stratosphere, it gets warmer. Okay, so these layers are based on the temperature changes. The mesosphere is warmer at the bottom, cooler at the top, and then the thermosphere is coolest at the bottom and warms up until you get to the exosphere or outer space, or there's different. Oh my goodness, it's Friday. There's different definitions, and also these altitudes vary based on the season. So there are seasonal variations to the depth of our atmosphere, and it's also variations based on what your latitude is above or below the equator. The atmosphere is deepest at the equator, unlike some of us, and then it's thinnest at the poles. Okay, and that has to do with the shape of the Earth and also the rotation of the Earth, of course. The ozone parts per million, we usually abbreviate it ppm, goes up dramatically in the stratosphere. Okay, so this is looks like about 7 or almost 8 parts per million. That doesn't sound like a lot, but it's enough to protect us. And the altitude again is going to be up pretty high, up in the 30-40 kilometer range. So let's see about this. That's probably good enough. All right. Again, ozone at the surface is bad news. It is created due to sunlight and pollutants from your car, or a coal-fired plant, or some other combustion device. This is a graphic that I showed you last fall when we were talking about electromagnetic radiation and how ultraviolet is part of that whole spectrum. And it goes everything from radio to gamma rays. Remember, the part that you get to see, the little sliver called visible light, is longer in wavelength than ultraviolet, has more energy. It's above energy than the violet light. And then, of course, there's infrared that has even longer. UVA has the longest. UVB is in the middle, and UVC is the shortest segment of the ultraviolet portion of the spectrum. And UVC is completely blocked by ozone if it's there, if there isn't a hole. UVB is mostly blocked, and most of UVA will get through. it's closest to the same length as visible light. If we have a hole in the ozone layer, that is a problem because that ultraviolet light gets down and can cause damage to your DNA. It's ionizing radiation. It knocks electrons off its things and can lead to skin cancers. The ozone hole, you'll hear in the next video, was discovered, actually I don't think it says who, by a team of British scientists that were working at the Antarctic. So we have a base, we've been one there for years on that continent, and they noticed in 81, 82, 83 that there was a really big drop in ozone. And they didn't know why. They published their work, and then people started looking into what was going on. And actually NASA stratospheric planes did analysis of the atmospheric gases, and they found that there was a change. There was chlorine bonded to oxygens up in the stratosphere. Didn't make any sense until we realized it was these bad boys, chlorofluorocarbons. They were a miracle chemical. They were used in everything from refrigerators and freezers to car air conditioners to home air conditioners to spray cans of all kinds, fire extinguishers even. It is a propellant primarily. It was used to expand foam, whether it's styrofoam or foam cushions. Turns out it's really bad stuff. And it was really amazing that we made this connection so quickly from first noticing the problem to diagnosing the problem to acting on the problem globally. We seem to be making progress, but probably on Monday we'll talk about that progress doesn't seem so good anymore. At any rate, I'll play the video and he'll talk about what's going on. Maybe.
In this video, you will learn about the famous hole in the ozone layer and why it has got thinner. We will also look at the action the world has taken to restore it back to health. To find out how stratospheric ozone is made and how it stops harmful UV from reaching the ground, view part A of this video. In the 1980s, scientists found something alarming happening over Antarctica during October when the sunlight returns to the South Pole after winter. The ozone had almost disappeared over large areas, causing the famous hole. An aircraft which analyzed the composition of the air flew due south 15 kilometers above the Earth in the stratosphere where the ozone is most concentrated. They found that the ozone there suddenly became replaced by chlorine oxide. This led to the realization that the chemicals called CFCs, chlorofluorocarbons, were to blame. These are inert, stable molecules and were once the wonder chemical used as the fluid in fridges and air conditioners, to expand polystyrene, and in aerosol cans to propel hairspray and paint and so on. They were completely harmless to animals. So what went wrong? Well, CFCs are so inert that they do not get washed out in the rain or broken down in the troposphere, so they diffuse up into the stratosphere. Use your knowledge about how ozone is formed to think about what might happen to CFCs in the stratosphere. Pause and think. Here they are bombarded with ultraviolet light, which breaks chlorine atoms off the molecule. These then bond with the free oxygen atoms, preventing them from reforming ozone in the ozone-oxygen cycle we saw in the first part of this video. When the chlorine oxide meets yet another oxygen atom, molecular oxygen reforms, leaving the chlorine atom to continue to remove more atomic oxygen. These chlorine atoms are eventually removed from the stratosphere naturally, but not before they have captured thousands of ozone-forming oxygen atoms. Thus, the ozone-oxygen cycle was being destroyed and the ozone layer was thinning all over the world. Thus, in 1987, the Montreal Protocol was signed by all nations of the world, banning the production and eventually the use of CFCs. They have been replaced by HFCs, hydrofluorocarbons, a similar molecule which contains hydrogen in place of chlorine, making them a little more reactive and so able to be broken up in the troposphere before they reach the ozone layer. Because the chlorine is slowly and naturally removed from the stratosphere by complex photochemical reactions, and because the ozone layer is naturally reforming all the time by the action of UV on oxygen, we expect the ozone to return to its original level in 50 or 100 years' time. The hole in the ozone layer allows harmful UV radiation to reach ground level, which can cause skin cancer. However, a common misconception is that it lets heat in and causes global warming. This is not true. Ozone is also generated in the troposphere by a complex series of photochemical reactions on the products from vehicle exhausts. Here, in the troposphere, ozone acts as a greenhouse gas and helps in the formation of photochemical smogs that pollute certain cities worldwide from time to time. For example, Los Angeles in the USA and Beijing in China.
So the hole in the ozone doesn't cause global warming, but ozone itself is a greenhouse gas. It's kind of crazy. So, and also people get confused about, kind of mix this up because it's about the atmosphere, and so they must somehow be related. It's not. It's a different problem. But from 81 to 83 and then 85, we figured out what it was, and then 87, developed nations put into effect the Montreal Protocol. But during the 80s and 90s, the late 80s and 90s, it was styrofoam was evil, and refrigerators, so they rely on a gas being compressed. There's a compressor, like if you leave your door open too long trying to figure out what to eat, the compressor comes on. That's because there's all these little tubes. If you have modern refrigerators and freezers, all the tubing is sealed and you can't see it, but there's a closed system, and old people like me know that you used to have to defrost your freezer because all the pipes, all the tubing would be on the outside and water would build up on them and ice over. And, yeah. Thank goodness we don't have to do that anymore. Anyway, that compressor compresses the CFCs, or used to, and then when they expand, I don't know if you've ever sprayed a spray can for very long. Hopefully you're not out tagging stuff, but it gets cold, okay? And that expansion is how your refrigerator and freezer works, how your car air conditioner works as well. So years ago then we had to switch over to different refrigerants in your car automobile, and you have to capture them as well if you have to get a reload of refrigerant in your car AC, or your refrigerator needs to be repaired. The technicians are now required to capture it so it doesn't go off in the atmosphere. Yeah, anyhow, so ozone holes are a bad thing that lets ultraviolet light in. This is a color-coded image. So Dobsonian units are kind of like Doppler radar. It's kind of the same thing. It's like an echo, and you get this image of there's no ozone basically, or very, very little here. So this isn't 0, it's 200, and red is twice that. So a very, very thin ozone layer here, which means if you happen to live in Australia, you're close to getting, these other areas are thin as well, and you're more likely to get ultraviolet radiation and skin cancer. So 79 is the base level that we use to measure how the ozone hole is doing. And this is 79. And again, October in the southern hemisphere is spring. Northern hemisphere, it's fall because of the Earth's tilt. So there are natural seasonal changes due to our path around the sun, our tilt of our axis, and our rotation. But taking those measurements at the same time each year, 79, 84, 89, 94, 99, 2000, we can tell that there's a big drop, and it even gets even lower. So this dark maroon color is 100. Okay, so a little different color coding than the last picture. I'm going to stop there, and we'll have to come back to this on Monday. It's a really important, like I said, environmental issue, and I do want to educate you about it. But I have a quick little one question sign off.